surface velocity of the glacier. So there's the question. Here's the linear features being detected manually, so again you can see that a lot of the linear feature pattern that we can see in 2003, you can see similarly in 2005. So we tried this both ways. We tried by delineating these linear features manually and then looking for comparison between the 2 years. We also tried a purely automated method, and this is the output of the automated method, in fact. So again, I've got the slope shaded LiDAR data as the backdrop, and then these red arrows here are generated by a correlation method comparing the data sets from 2003 and 2005, and these are velocity vectors. There's the scale. So if an arrow is that long, it means that the average motion between those two data is 3 centimeters per day. So you can see that typically these are coming out as typically 2 centimeters a day, I suppose, 2 centimeters per day, and that reassuringly the velocity field is downhill. What's in yellow are some, I shouldn't say velocity speed contours because there's no direction here, derived by Dave Ripin, very laboriously in his PhD work by measuring stakes in 1998. So you can see the particle in here has a speed of 1.5 centimeters per day and a little bit more. So there's a lot of consistency between the velocity field that we were finding in the mid-2000s and the speed field that Dave Ripin was finding in the late 90s. So that's rather encouraging. So, putting this into a different kind of context, and this is where I'm borrowing rather heavily on Neil Arnold's work. Well, we worked together on this actually. We know how this glacier is retreating. We know where it's retreating. Can we understand why it's doing that? Well, the best way of answering this is with an energy balance model, which is actually doing the physics. It's actually considering how much heat the glacier receives, how much melting that will cause. So that's quite a complicated calculation. It's to do with the air temperature and the wind speed and the rate at which energy can be transferred from the atmosphere to the surface, but also directly from the sun. So you have to bring quite a lot of things into this, but one of the things you need to know is the surface topography. And of course, now that we have the LiDAR data, we have unprecedentedly detailed surface topography. So we're kind of entering a new, or 5 years ago we entered a new era of being able to do these energy balance calculations. So that's pretty exciting too. So here is the sort of input to that process, but it's nice to look at. This is a calculation of the direct receipt of sunlight by the glacier. So it's a three-dimensional, somewhat vertically exaggerated representation of the glacier surface there. You can see the surrounding rock, and here is the shadow being cast by this mountain on the side here. So we are able to calculate pixel by pixel with a 2-meter resolution which parts of the glacier are receiving sunlight and which aren't at any time of day. So this is the calculation for 1st of August, some year, at 21:30. So we can do this minute by minute. In fact, we do it half hour by half hour throughout the course of a year to work out which bits of the glacier receive how much. So here is the result of a calculation like this, like that. This is the energy input in megajoules per year. There's a scale bar for it. So you can see what you can see rather importantly is down here at the snout area. This side of the glacier, which has got a slightly bluish tinge to it, is receiving rather less solar energy than this side of the glacier, which has a rather more yellow tinge to it. And it is indeed melting faster on this side than this side, and we're just at the stage of starting to tie these together quantitatively. So as I say, this part is done by Neil, rather than me. We've got as far as this, saying that the energy balance approach shows a strong correlation with the observed pattern of mass loss. Okay, I think this is probably, I might get a bit early. This is probably my last slide. It looks like the last slide to me. So where have we got to? LiDAR, we haven't got to the bottom of how much information is glaciological useful information there is in this kind of high resolution LiDAR data, but the answer is clearly a lot. We know we can do a lot with it already. We can certainly do mass balance, but we can also resolve temporally stable surface features that we can use for velocity tracking. What we find from that is some take-home messages about this particular glacier. It's moving down slope at about 5 to 10 meters per year, carrying some surface features with it. They seem to have a persistence time of 5 years or so. We looked for them again this summer. Some of them were there, some of them weren't. It's losing mass currently at a rate of 0.4 to 0.7 meters water equivalent per year. Its snout is retreating at 6 to 10 meters per year. These are all things consistent with what energy balance modelling tells us that we expect it to do. So, in summary, it's a powerful, comparatively new technique for quantitative glaciology. I think. Oh, that was my last slide. Okay, right. That's the cloud company. So I've got a minute for questions.
I have one question. One of your slides on the, you want to show the surface motion?
Yes.
And actually a few others as well before that. There seem to be some darker depressions in the LiDAR data. Maybe that was near the head walls. Is there an ice fall there, or is that where it's more highly depressed?
Are we looking
Yeah,
here?
in there and to the right. There's a bowl-shaped area right in there. Yeah. Right.
No, it's real. But it's a consequence of the particular way I've applied the slope shading algorithm. This is what that's actually saying. I've illuminated this from the top left, as it were. So what that dark bit there is actually saying is that that's actually a pretty steep slope there. This part of the accumulation area here is actually quite a bit higher than this is here. So again, we've got quite a steep slope right there.
Well, I was wondering if that would, could you see any zones that might have increased melt in depressions or have a faster ice flow out of?
The LiDAR data actually gives you, well, it depends on the kind of LiDAR, but this one certainly gives you two pieces of information rather than just one. It gives you the timing and hence the range of the aircraft to the surface and hence the height of the surface, but it also tells you the intensity of what comes back. And that is certainly different in different zones, different facies of the glacier. And that's something that we looked at a little bit, and it looks as if it's got somewhere to go, that's actually quite useful. And what we're hoping is that we can actually combine that with an analysis of sufficiently high resolution optical and near infrared data to get a real grip on the facies and surface zonation. And that's, I don't want to steal too much of Alan's thunder because actually a lot of that is his PhD. So this is an area that's very interesting to us certainly.
And were you able to take into account precipitation changes over that time as well, just to think about the mass balance?
We haven't done anything about that. I mean, we do talk to Jack Kohler, who is the source of the mass balance data, and we need to talk to him some more because, of course, what we're looking at there takes us up to 5 years ago, and it's been 5 more years of growth and decay. So we need to put it into that context. Certainly, that's true. Yes.